Welcome to Math 2318, Section 1.8. In this section, we begin to look at linear transformations. And we're going to see eventually how linear transformations and matrices are tied together. So what does it mean to be a linear transformation? Well, t is a function. T is a function going from Rn into Rm. We pick a u in the domain. T of u is a v in the range. Now, to be a linear transformation has to have two properties, and that is t of a sum must be splittable as t of each of the pieces. So again, that must be true. And t of a scalar multiple of this vector u is equal to c times t of u. And what that means is, when you put these together, is that t of the origin must go to the origin. So t of 0 must always be 0. So for example, take the function f of x is 3x. We're going from R1 into R1. Is it linear? Let's see. F of u plus v is 3 times u plus v, which we can distribute. I get 3u plus 3v, and I get f of u, and I get 3 f of I get f of u plus f of v. So yes, it is linear. What about f of x is 3x plus 2? Well, this is not linear because f of 0 is not 0. So if t is my transformation from Rn into Rm, there is a matrix A of size m by n where I can define t of a x in the domain of Rn as matrix A multiplied by that particular x. And you can check that the sizes work out, because if A is m by n and x is a member of Rn, x is n by 1. So the matrix multiplication makes sense because the number of columns of A matches the number of rows of x, and the size of the image is m by 1, which does put it into Rm. All right, in question 1 here, we have matrix A. And matrix A is 2, 0, 0, 2. And we want to define the transformation from R2 into R2 by t of an x is A times x. So what's the image of u and v under the transformation? Well, t of u is A times u, and t of v is A times v. So this is simply multiplying our matrix A by each of the vectors. And so this is simply matrix multiplication. And so t of u goes to the image of 4 minus 10, which, if you notice, is just 2 times the original matrix. And t of v is, when you go through the multiplication, 2a, 2b, which is just 2 times my original vector. All right, in question 2, we want to define a transformation from R3 to R3, where I have matrix A is 1/6 on the diagonal, and I want to find t of u and t of v. All right, well, T of u is A times u. And when you go through that, the matrix multiplication, what you get is 1/6 the original matrix, and you get the image of 2, 1, minus 5. Now if you do the same process for V, where V is F, B, and H, and again you grind through this, you see it's simply F, B, and H all divided by 6, or 1/6 the original vector. All right, in question 3, we have T of an x is A times x. All right, so here's matrix A, here's B. What I want to find out is it possible to find an x where T of that x maps into B? Maybe we can, maybe we can't. So to figure that out, I need to see if I can solve the problem A times x, because that's how T is defined. Does that go to this particular B? All right, well, let's see. So I form the matrix. I'm going to use this one to make some zeros. So did that. I multiply, I'm going to swap out the two rows. All right, and multiply this one by -1. So now I'm going to use this one to make some zeros above and below. All right. At this point, divide row 3 by -4. And I'm going to use this one to make a 0 above it. And so when I do row reduction here, missing a 0. So when I do that, I see that yes, there is an x, this particular x, where if I put that into the transformation T, I do end up with vector B. All right, let's see. So here we have T of x is given by this matrix times a vector. And so we want to put in u and v and figure out, well, what happens? Well, what is T of u? So it's this matrix times 5, 3, and we get -5, 3. So it's essentially the negative of the original vector. So if a vector v is pointing in one direction, so or call this vector A, then the reflection of it would be pointing in the opposite direction. And so where is it? Well, here's u. U is 5, 3. This vector pointing this way is the image, or -5, -3. The picture isn't particularly clear. I wish they would have had arrows on both sides so you could have seen that. So what happened to V being -3, 6? All right, well, let's see. -3, 6 is over -3, up 6. So there's V. The negative of it would be 3 minus 6, which is down there. And so what is this? This is a reflection through the origin. All right, so here we know that T, which is a transformation from R2 to R2, T is going to map 2, 4 into 4, 1. So here's U. It goes into U hat. So T of U is U hat. And V gets mapped into -1, 4. All right, so separate them here so it's easier to see. All right, so what happens with t of 3u? Well, because t is a linear transformation, this is 3 times t of u, which is 3 times the image, so 3 times 4, 1, which is 12, 3. Similarly, if I know something about what t does to v, then t of 2v is simply 2 times the image. So 2 times minus 1, 4, or minus 2, 8. And what does t do to a sum? Well, let's see. Because it's linear, this is t of each piece, and then the scalar can come out, and so it's 2 times the image of u plus 2 times the image of v. So we have each of those, add those up, and I get 10, 11. All right, let's see. So in this question, question 6, t is a transformation from R2 to R2. They tell us what t does to E1 and E2. If you want to think of them as I and j in R2, that's fine. So we know what t does to each of them. So, well, what does t do to 5 minus 3? Well, 5 minus 3 is nothing more than 5e1 minus 3e2. So t of this particular vector, because t is a linear transformation, is t of each one, and the scalar comes out in the front. And so it's simply 5 times the image of E1 minus 3 times the image of E2. So form those, add them up, and we get 18, 9. Similarly, what happens to x1, x2, a general vector x in R2? Well, that's writable as xe1 plus x2 e2. And so t of each of these, again, because it's linear, is t of each one. Scalars come out, and so it's x1 times the first image plus x2 times the second image. So fairly straightforward. All right, in our last question, we'd like to show that this transformation, which is defined here, is not linear. Well, the easiest way to see if something is linear or not is, does 0 go to 0? So simply plug in 0, 0, and what do we get? Well, that's 0. 0 plus 5 is 5. That's not 0. And the last is 0. So t of 0 is not 0. So in algebra, we talk about linear functions, but in actuality, the only linear functions in our case, in R2, are lines that go through the origin, because we need t of 0 to map to 0. You'll see later in future courses, often in physics, where if you have our typical linear function y equals mx plus b, that has a different name. It's an affine transformation.